Test. Test, test, test. Okay. Oh, would you please confirm if you hear?
Yes.
And also try if you can speak and we can hear you.
Yes, we can hear you. Okay.
Oh, Hanman, can you please tell if you hear?
Yes.
Yes. Can you
Yes.
speak something so that we recognize your voice?
Yes, I can hear you, Dr. Kelly.
We don't hear. Let's quickly test. Speaker number one, please speak.
Yes.
Doesn't work. Number two, please speak. We need your voice.
Yeah.
We don't hear you. Speaker number three.
Do you hear me?
Not here. No, we don't hear. Speaker number four.
Do
Please
you hear
speak.
me? Do you hear me?
Okay. Lola, would you please try speaking something, and I will quickly try different speakers. I'm going to go through 3 speakers. Speaker number one, please unmute microphone and tell something. Maybe she just logged in and left the room.
Yes.
Okay, then if you have questions, you need to type them in the chat line. Okay, thank you much for coming. And I really appreciate you coming in person, because you see even good technology sometimes fails. As our meeting goes on, I will probably bring a list of subjects that we need to go over on our first presentation. Presentations, which will be like analog of midterm, when we chop basic skills onto like amount of participants and you do brief report of what they are. By now, in our previous meeting, we have covered the basic login to service and server and working with files, right? And I don't know if we have finished this or one can add more details, but there are generally 2 more categories. So one category, which is important, but sometimes in some years we were even skipping it from the first presentation. The concept of computer clusters, of supercomputers, and how to operate them. Even if no one selects it, and if I do not show anything right now, we all will go through it naturally. And some of you do like CCast cluster, right? You did it in your rotation. The most important thing that is unavoidable is building chemical models. And just in order so that I do not waste time on bringing up slides, I'll probably go directly to it. And later on, we will discuss how we chop this information on pieces. So a molecule is a collection of nuclei and electrons. Electrons moving so quickly that a computer program just needs to know their number, and it will distribute electrons over orbitals and shapes. But ions needs to be specified quite precisely. Even if there is a reactions and ions are moving over time, they move not so far. The skeleton, the backbone of a molecule needs to be defined by a human, right? There are several alternative ways. So drawing a molecule by specialized software is the good starting point for everyone, but there will be alternative ways of downloading the structures from databases, because a lot of researchers publish their structures. And these structures come from several experimental techniques. So it's not my and your problem in this class, but generally there is a single crystal X-ray crystallography that allows. So if one can crystallize a material, if it is like bulk crystal or even biomolecules that stack into crystals, then based on scattering of on X-ray diffraction and looking for the signal, one can reconstruct positions of all atoms. And then this coordinates of atoms can be imported. So maybe it will be one of the presentations, like where to take these files and how to make them doable for what we need here in class. But we'll go the golden middle, just how to click on mouse and draw a molecule. And it will be chopped onto maybe like 6 talks, like how to change angles, how to change distances, how to copy paste different fragments of a molecule. Pieces of software. We all will practice and train so-called Gauss view software. This is considered as an ideal gold standard for a chemist. And it is criticized from 3 sides. It is criticized by theory developers because it is not open source. It is criticized from materials engineers because it is not ideal to describe periodic systems, and it is criticized from bio engineers because it doesn't have all options for docking. But still, it is a good starting point. So graduate students, well, the majority of this class is graduate students, so I need to give compliment. Graduate students is intellectual elite of the globe, but undergraduate students are seeds of the global elite, so that everyone gets credit. And you may find things that I'm going to deliver yourself just browsing through internet, and it is completely open, completely welcome. So if you look for the keyword Gauss view and find anything, just learn and either challenge me with questions about it, which is quite easy. I'm not primary expert in Gauss view, or just increase your own knowledge or create an idea what to envision. That's okay. That's okay. So you'll find what to look at. So just Gauss view. We will cover these namings later, but I just cannot constrain myself from telling stories. The electrons like to sit in the atomic orbitals that look like orbitals in hydrogen atom. And mathematically, they have sharp features near the center of ion. And computationally, one can approximate these functions with sharp cusps by Gaussian functions and their derivatives, which are, from point of view of calculus, are good functions, continuous and no cusps. And this trick gave a name to a code, Gaussian, and then which just does the job of computations. And it's like nephew Gauss view, which treats input and output of the Gaussian. So the 2 different codes. And we're going to do it. So what we are going to do today is to log into Photon server. It has a Gauss view, and we will just practice drawing molecules. I think I already started announcing the homework for the next week will include an invitation to draw quite complicated molecule. I understand that it is not possible to do ideally, but it's like a challenge. You'll try to draw it, and it will have the fragment of carbon nanotube, which is much better to find in the database rather than draw by hand. Anyone who will try to draw by hand will get irritated and upset, but we just need to keep going. What else? Please raise hands who use Mac OS on Macs. Who plans to use one? Only one. Mac, Apple Mac. No, so only one. And you use Windows on the Mac. Okay, you're the lucky one. I'm probably talking too much, but it's better if we, in a freestyle, discuss all things and then I'll focus on details. Macs are really cool, but they are not standard in a thing. And what we are going to practice today is, in comparison to our last lab, in addition to just chatting to a computer by a text, we are going to do graphical information processing, which means we will do mouse-operated procedures, not on the local laptop that is in front of us, but on the remote computer. So it needs additional software that tunnels or funnels or transmits graphical signal. MOBA Xterm that we all started does have this option, and we will do it seamlessly. But if you are using Mac, transferring graphical information is not as easy because they are trying to be super secure and preventing any strange information. So just I'm giving you heads up. And if there will be any delays in running graphical applications on Mac, and it will be too hard to overcome it, just use the local station. Sarah? If something will not work, just use the class computer. Okay, good. The Photon server would be our preferred tool to learn things, but there is an alternative way for those of us who are registered employees or students at NDSU to get Gauss view through CCAST. I will not. It's better to have several options. Okay, okay. But I just want to show this option as well, so that you feel more tools in your arsenal. Okay. What other backup plan B things are available? Our goal is to build molecules, and I will go into actual thing very quickly. Purchasing Gauss view and installing it on each computer is possible, but it's economical question. When it is installed on one Linux server, then we all can use it for the same license. So it's basically just the way to save. But sometimes one may want to have something in hand on the personal laptop. So Gauss view is good, but is not the only one who does this job. And there are a couple of other recommended pieces of software, which I probably will not have time to show and practice, but it is a really good way out. So one of them is Avogadro, which is fully free. So same as Avogadro, same as Avogadro number, right? And you type Avogadro software and one can install it on personal computer. It will do the same job of building molecules, creating models, and then sending them for calculations. Another piece. Well, this will be enough. And later on, we will get some other pieces of software that are mostly used not to build the models, but to analyze the output. Just JMO, VMD, and Vesta. And I think those of you who are doing materials engineering already play with VMD, right? Some of you do it, right? No one? Okay, good. Can we use materials? Well, I don't care which software you use. We will. It's just outcome based. If you can do better model with your preferred software, that's great. Chat line. Okay. So I'm going to share screen. And before we go to actual thing with Photon server, continuing what we did last time, I just quickly want to show this option of Gauss view on CCast. So we, as NDSU employees, our university ID is expected to work to access this supercomputer. And there, on this, I just sent a link, there is a so-called on-demand concept. So if one goes onto this on-demand, I'm also going to share a link. Copy, chat, paste. So there are several graphically intense applications that can be run on CCast server. And if I click on this Gauss view, it will ask, I can do it once again, tab. This is graphical operation of the concept of interacting between humans and supercomputers. So briefly, the making a single computer more and more powerful came to its saturation. And if you look for clock speed or like performance of individual CPU, it stopped developing like 10, 15 years ago. It can just by a few percent. And currently, the commercial avenue of making computers more powerful is just putting more CPUs on one board and putting several nodes interacting with each other. So this architecture, which is like you have multiple CPUs on your laptops, like 8 cores, right? Or like 4 cores. But it's still not enough. If one make a stack of 100 of your laptops or 100 of those boxes and make them to work cooperatively as a team, it will be a supercomputer, a cluster. And there are multiple CPUs and there are many users, humans. So humans, if it is too expensive to work for one human, so the resources is shared. So several people are using it, and there is a specific program called scheduler which distributes resources. So we will do all the things in a command line. But as a simple example, there is a graphical option. When so going through this link, requesting that I want to use Gauss view, and then I tell I want to use it for 4 hours. So after 4 hours, it will be broken, even if I didn't complete. Probably it may not work right away if you do not have this link, but we can arrange it. I can put you in the user group if something doesn't work. And then after setting these things, I click launch, and then it waits in a queue. And then after there are available resources on the supercomputer, it gives this option to launch. And then there is a graphical access to a software that we are going to use. So you see, I'm building a molecule by clicking, and one can rotate it, do different things, and save it on the disk of this CCast cluster. So I'm briefly showing this option, but it is not that I will ask everyone to do. It's only a backup plan. Primarily, we all will just do things on a much more humble little server, but there we have access to all opportunities. And if something doesn't work, there is a person who is responsible for making it work. That he's in the crew nearby, and we can ask him to help immediately. Okay, so Sarah did practice this Gauss view on CCast, right? We will select what is better. And you've got, we are on recording, and you may try this option if you do not like Photon as a way out. Okay, now yeah, I'll talk to the system manager of the CCast and make sure maybe everyone in the class is added to use it. But right now, let's go through our standard thing. So we all have downloaded mobile Xterm, right? And in the mobile Xterm, I am, scroll up. There is an important thing between the command SSH and user at server. I add the -X key. So it can be either -X or -Y, and it is this abbreviation does serve for the letter X is used in Linux community for transferring graphic information. Like when we met previous Wednesday, we were only typing commands as a text. Those of you who have some experience and you were asking about WinSCP, there are alternative ways. I will not memorize all of them, but mobile Xterm is a software of choice because it easily implements graphical tunneling. There are like 100 other pieces of software, but they are not as good on graphical tunneling. So after I go through this command, logging in and going to the directory, subdirectory, which we have created, each of us has created for this class, right? So just in case, if copy, paste, and I will copy this line into the command line, paste. So here's the list of attendees of the class. I'm going to my subdirectory. And if I really want to be organized, maybe I can do make directory lab 2. But I don't care. It's just it's so easy to get swamped without organization, but it's just personal matter. Okay. And now in here, I'm typing gview exe and then symbol of this ampersand. Things will work without this symbol at the end, but if I do not type it, it will block my command line from entering any other commands. So I better put it here. If you have curiosity as a future Linux gurus, then type which, and it shows where this executable is located. We do not need it. It's the path is already there, but if it's just for curiosity, and if something doesn't work, we can look in this directory and see more things. So I already typed this gview exe, and then I'm getting the page like this. So let me go over your sites and see if so basically there should be 3 windows. One main window with options to like save and different panel as in many pieces of software. Then often it's automatically pops up the periodic table, and most important, a panel where one can draw molecules. So just try clicking on this panel and see if you can like go from methane to ethane, or choose an atom from periodic table and see if you can do like substitution. So just go ahead with this little plane, and I will make a circle over the sheets and check if it works at your sites. Don't hit enter. Wait.
SSH.
Yes, and let me check the spelling. Okay, good. Yes. SSH space minus Y X A. Okay.
Right.
Yeah. Enter.
This is password.
Enter.
Why is that?
It will not type. The passwords are considered secret and they will not pop up. So hit enter when you're done typing it.
Oh, got you.
If you type it wrongly, it will complain.
Right, got
So
you.
retype. I'm not sure if copy paste will work.
Let's try.
Let's type.
No,
No, the copy paste may not work.
yeah, I know.
No.
No.
If you are system administrator and if you're installed it forever, then you can answer yes in the future. Now navigate to the directory, and then from there run goes you. So I think John is successful in doing things. So if something doesn't work, ask him.
Sure.
Right?
Fine, thank you.
Okay.
I was able to log in and then
So I went through several sheets and observed that going to right directory is like a little challenge. Let me write it down so that you feel more comfortable. So browsing through directories can be made in one piece or step by step. Those both work well. So one can do in one piece, lowercase c, d, then space, then slash, scratch 0, 0, 1, and I'm continuing long line. Chem 4, 7, 6 slash chem 676 2022, and then hit enter. Sometimes, especially at the beginning, one can feel upset if you type the whole line and things do not work, right? You start like, computer, I'll break you. So one can do by step. So CD space slash enter. Then you do ls, and you see all directories. And you see among this directory this scratch 001. Then you do cd space scratch 001 and hit enter. And then you do step by step. You go to next door, make list, see what are the opportunities, and go to the next one. Okay. So I'll continue a trip along sheets.
I went to my folder
Okay. Okay.
and then
G view dot exe space shift 7 enter. And do not worry, it will be,
Oh,
yeah,
yeah.
here it is. And try click here, and then point on the hydrogen, and click once again, point on another hydrogen. And if you're bored with this methyl group, select something different from periodic table.
Oh, okay, all right.
Good. Gview. Gview dot exe space shift 7 enter. Let me wait and see how you enjoy it. And the most important is the last one, the white one. Yeah. So just try clicking in the middle. Now click on the hydrogen. No, right here. Click on the next one. So methane, ethane, propane, right? And if you're bored with hydrocarbons, you can change the type of bonds from single to double. And if you're bored with carbons, you can select something from the periodic table.
I need this dictionary by that kind
Okay.
culture.
Yeah, I need to talk to system manager of CCAST so that he ends everyone in this class to the Gaussian. But here, PWD, CD, and so we do not have X server.
I think I should tap the.
No. In the Mac, things are different. So maybe for quick, we'll do things here. Let me check other things quickly. Where are your applications? Can you navigate me to applications folder on Mac?
Applications.
Okay. Is there something starting with letter X?
X.
No.
No.
Utilities. Okay, yeah, it's not there. If there will be enough users of Mac, I will show specifics how to deal with it. Let me. So what we can try doing. No. Yep, it's better to do, but I'm aware of this problem and I have an idea how to resolve it. It will be just for today quicker to run it on PC. So you remember MOBA X term.
What?
MOBA X term. Let's do it together. Okay, and then keep going. Hello, Hailey, how are you? In Avogadro. Okay. Do you have access to Gauss view? Eh, Okay. How? Yeah, that's fine. But how are you going to access Gauss view if you are not in your office? No. Well, you can use Avogadro, but it's better if you have access to the same software as everyone else. So just as an exercise, maybe try to look into this one and use mobile extern. Let's do it together. You do?
I use a virtual environment. so-
Okay, then everything will work. Let's. Did you do? It should be uppercase X. I am. It may not work. Then we would redo. G view. Yeah, it doesn't want. So let's reconnect once again. No. So exit. Exit. What? Okay, it works. Right now we are in the wrong directory, but we can fix it later.
Okay.
So you have access to. Okay. No. CCast is for future. Which one? Okay. View. So there are 3 windows, and try to click in this white space. Click. Now click by yes. Now navigate to one of these white spheres onto hydrogens. So this one is methane, 1 carbon and 4 hydrogens. Yeah. Now click on the hydrogen. Click. Okay. Now click on another hydrogen. So you're going from methane, propane. And if you're bored with carbons, you can select other things from periodic table. But now we can do it without CCast. Okay. Which one is yours? Uppercase? Oh. This one? Okay. So click in this white space. Select on hydrogen, click once again. Select something from periodic table, like chlorine, oxygen, whatever. Click on hydrogen once again. Okay, so you can build molecules. Just. You also have Mac? No, it is what I was telling you. So I will need to tell ideas how to enable. Okay, I'll continue work after doing some suggestions. So sure, I told you that from Mac it is not as easy. So one, I see there is a population of users who use Apple Macs, which is okay. I'm using it myself, but is not as natural to have graphical connection. So one of the options, you can learn from Haley how to install a virtual machine, and then from virtual machine you do absolutely the same as you would do on PC. So Haley just teach anyone who asks you how to install virtual machine, how you did it, and then you just repeat the same thing. It's maybe not very efficient use of resources because it's like the computer has a schizophrenia. It works on one part of the CPU as Mac, on another part as a PC. But our tasks are not as hard. So another way that works, let me quickly share screen from the different equipment. So I stop sharing here and we'll connect from another one. So share screen. There, one needs to install so-called X Quartz application. I will not go over all details, but the symbol is here. Just type X Quartz, and in the X Quartz application, there are ways when you configure it. There are ways to have graphical tunneling and open terminal, which is different from standard terminal of Mac. It overcomes firewalls and allows to use graphical application. And from the X Quartz terminal, one can do SSH no, I need to reconfigure it, but eventually through this, demonstration was not as good. But there is a way to get graphical connections through the X Quartz. The thing that we found working today was the virtual machine by Haley. And the third thing is to get the connection via CCast. That also needs some additional steps so that system manager of the CCast enters you into the system as users of Gaussian. Okay. If you need to run Gaussian right today, the quickest way is just to use this in-class desktops, because the MOBA Xterm does not require system manager privileges. You just download and run. Okay? Is it virtual machine? Directly MOBA Xterm may not work on it's. Huh? So here, download. 30 seconds. Let's put open and down. Okay, should be done now. I'm just impatient, but it should be here. Okay, so opening, extracting from archive, running. Start local terminal. So which one is yours? GView. Try clicking in this white space with the mouse. Try to navigate to hydrogen and click once again. So you're doing polymer of hydrocarbons. And now try to select different element like whatever, oxygen. Okay, so you can. Did it work? Okay. Yeah, that's good, but try run mobile experiment on this computer. Yes. Hmm? Whatever is comfortable for you, I just. But mobile experiment will be quicker. So I'm working on trying it. Mobile X. No, but it downloads within like 30 seconds. Quick? No. This is free. So select open when ready. I'll be back. Okay. Oh, no, you do. So you look through things that you have here.
So it's just the install version.
Huh?
I have installed that cause you,
Oh, you already have the Gauss here.
but I'm not getting there.
Yep. But
So what is the problem? I don't understand why some people doesn't have this.
just a second. I make sure it works, and then thank you. I'm fine. So just click in the white space. Click. Now click navigate in hydrogen. Click again on different. Now select something from periodic table like oxygen or chlorine. Click also on something, so you can build molecules, right? Space minus X. X capital. Uppercase X. No, select no. Cancel and select no.
It's really hard.
Uppercase. It starts with uppercase. Or lowercase. Okay. And now type GView. EXE ampersand. and just bring them up. They're here. All three. And click in the white space. And click on hydrogen, just make sure that it works. Click on hydrogen here. Now select a different element like nitrogen, carbon. Select like carbon, click on hydrogen. All works. I noticed you had.
Yeah, I'm just trying to see what the stuff does.
Okay, yeah, thank you. So let's go further, but by now you all have basic skills. Oh, let me quickly check with those online. So Hemant, would you please share your screen? Let me check if you are co-host. My co-host, yes. Okay, please try sharing screen now. Okay, please bring the white panel and or yeah, not the. You can share your whole display. It will be much better. Okay. And just can you show how you build bigger molecules? So click on your like atom number 2 in your model in white space, in the white space, where you have yellow circles. Click on, yeah, click here on hydrogen. Okay, everything works. Excellent, you can stop sharing. Thank you, Hemant. And I think, Lola, you have all skills at hand, right? So now, what do we do? What do we need to do? I'm going to chat for another like 5-10 minutes. What would be our most natural next steps? We need to save and load these models. Even if you're not going to run any calculations, we need to make sure that this models are saved. There also, we will try to modify the models because Gauss view software has some, I wouldn't say intelligence, but it uses databases on most optimal and typical distances between specific pairs of atoms. But sometimes we need to go crazy and model situations when they are not standard. So we need to be able to expand or contract models before we go forward, or modify angles, or create something that is different from standard. And this will keep us busy for some period of time. But so saving, loading, modifying parameters of a model. And there is an additional chapter or section that I have forgotten to declare, but we will definitely do it. And it will be another piece of software that is called Babel. Babel. So I even do not know if we will have time to work with it today, but after we have enough, we satisfy our curiosity and play enough with modifying models, saving and loading, we will need to practice the Babel software. It is our next milestone. What does it do? We cannot believe that creators of the Gauss view software were the only people on the earth who did computational chemistry, right? They had competitors, more or less competitive. And each person who is trying to do the same job has its own his or her own specifics, how to do job done. So the files where we save these molecules have slightly different formats. And if you want to be universal soldiers, if you want to speak with different communities like physics, material science, biology, chemistry, they have preferred formats. And some formats that are created by Gauss view are not recognized in, let's say, physics community. So the Babel is a translator command which converts atomistic models from one format to another one. So if at some point we need to use different piece of software, we can use Babel and be universal. So after we are done playing with geometries, we'll go through it. There is another thing that I'm not sure if there will be enough time to speak about it in details, but I want to give an announcement so that you have the whole picture, and I'm playing the open cards. So how these atomistic models that you have already created are stored in the memory of computer, what they actually are, how big these files. You all did beautiful models, which were like three-dimensional spheres, rods that launch our imagination. And making three-dimensional pictures of this complication would be big graphical files. But in fact, the files to save structure are very tiny. They are few bytes. They're even smaller than letters, emails that we write to each other. The actual information that is being saved is only type of element and 3 Cartesian coordinates, x, y, and z. The next element, x, y, and z. So if you have like benzene molecule, it is expected to be like 12 lines, 6 positions of carbons and 6 positions of hydrogens. That's it. In different formats, sometimes creators of software add additional information. For example, how many neighbors this atom has. And then if all atoms are numbered, then like I am now atom number 1. My neighbors are 12, 16, and 2. But it's still not too many information, right? Okay. And I'm not sure how favorable I will be able to spend time, but if we will go quickly over all things, I would like to convert some models into the simplest format, which is like XYZ format, which omits all unnecessary information, and then merge together your experience from last Wednesday and today, when we will open atomic coordinate files in the VI command line and see if we can edit it. The original way when computational chemistry was designed and created, there were no tools for graphical manipulation. There were no mouses. Mouse was designed very late. Well, for us, it looks like several decades before, but there were so many developed industry and successful computer programs, and everything was without mouse, without graphics. People were just typing codes. And early stage software that was already successful, all operators of the software were just typing coordinates of atoms. And when like molecular dynamics was run, they were opening files and reading coordinates of atoms. So making graphical things is very late addition. And we will try to make connection just to be powerful and be able to manipulate geometry without a mouse. So this is a goal. I cannot promise that we will reach to this stage today, but it would be nice to. Okay. So please raise hands who is major in chemistry. 1, 2, 3. And I think Lowell is also major in chemistry. So you will be experts. So raise your hands once again. Don't hesitate. And everyone in class, look at them. If you have questions in reliability of chemical structures, ask experts, because everyone in the room is like intelligent researcher, but some people got additional training. And some, when we draw something, it can be reasonable chemically, or it can be something that looks beautiful to us, but the mother nature will never realize, will never build. So there is a concept of number of bonds and coordination. Like right here in this model, we used this carbon connected to having 4 bonds, tetrahedral. But it's not the whole story. One can use the oh no. Carbons and hydrogens with different number of bonds, right? So triple bond, double bond, and then number of hydrogens is changing. So if you click on hydrogen, which is most important element for chemists, it has several patterns, how many bonds it has. Like simplest one is maximal number of neighbors, typically placed as hydrogens, but there are other things. And most interesting for organic photovoltaics, for OLED TV panels, is this one, conjugated bond. So we can see it in benzene and in many so-called conjugated polymers that work as conductors of electricity. So like non-metal metal. So based on carbons, one can do conductive wires and do all electronics. No silicon, no metal, only carbons, hydrogens, and maybe just few nitrogens. But then one needs this conjugated bond, which allows electron to funnel through without resistance or with minimal resistance. So while building models, we need to recognize that molecules, atom in a molecule may have different coordination. And not every piece of software has this information, though few does. In other pieces of software, one needs to guess and use chemical intuition. So the central panel shows which side of this fragment will be applied to a new molecule. And it automatically complements things. So this is also something to try. Okay, now I'm going to focus on these 3 buttons, which shows like a dumbbell, letter V, and then I don't know which letter is this, which tells bond, angle, and dihedral. If I have too many molecules, I can just start new model over again, or use this little X. Okay. Something simple. Carbon. Okay, so first option, the bond distance. One can, upon selecting this bond distance, one can select 2 atoms. They are getting numbered, right? And then it measures what is the distance. If we draw, then the distances are automatically set. But suppose we already did a calculation and we want to learn about geometry of a molecule, then we can read geometry of a molecule into Gauss view and then measure what was the optimal distance between certain pair of atoms. But if we are in the creation of a model option, we can click on this tab and just expand model and see, okay, let's do a molecule where two carbons are 3 angstrom from each other. Likely upon optimization, it will break onto fragments, but who knows, maybe we need it. Or we can place them really close together. And then if you run optimization, they will be just broken far away because of repulsion forces. And one can just explore, do several models and save at each value, and then explore how the geometry depends on interatomic positions. Basically reconstruct potential energy surface. There is a way to do it automatically, but one can do it also manually. Just create 20 models with different distances and then run 20 calculations and store total energy. And right now we are moving both fragments, fragment 1, fragment 2. There is a way to fix number 1 and move number 2. So in some cases, we need this versatility. Okay, and if your chemical intuition or the problem that you are solving tells that there should be no bond or single bond or like specific order of bond, one can change it here. When we will do true ab initio electronic structure, this bond order means nothing. But at the preliminary stage, when we will do force field molecular mechanics, which some of you in engineering practicing every day, then this bond order is critically important because I will try to cover it in lectures. Force field molecular mechanics knows nothing about electrons. It uses tables, it uses fitting functions for interatomic forces. And the interatomic forces depend on the order of bond. So we need to know about order of bond between pairs of atoms to correct the forces correctly. So if you think that you will ever do force field, then be very careful about putting bond order. If you're going to use like semi-empirics, DFT, Hartree-Fock, MP2, couple of clusters, you don't care. Just positions of atoms are fine. Okay, and I think it will be one of the presentations. So someone select this and just tells a story about changing interatomic distances. Okay, saving, just file, save. So I want to be in lab 2 in my subdirectory. And now I need help of professional chemists. So I'm saving a molecule with 3 carbons, but it's like not propane because the central one doesn't have all bonds. It's like 1.5 bond order, right? So I can either type that it is C3H8. No, it's H7, I think. Or if experts will give me a prompt, I can type some chemical name. John, how would you call this molecule? Okay. Protein. And then there are options to select different names. So Gaussian input files is .com. And it is standard if we are planning to use this model later for Gaussian. But if you are going to communicate your model to colleagues who do not have chemical background, more standard thing is PDB, protein database. It's originally designed for proteins, but it is extensively used in all areas of science. Gaussian format, save. And now if I look here, I do see that I do have a file C3H7 propene, and I can look inside, and you recognize there are some keywords before and after, but in the central part is basically a list of atoms, and for each atom there are just X, Y, and Z coordinates, right? And if I want, I can just open this file with VI, change coordinates, and the atom will be placed on a different place. So probably I can do it right now. So I copy just in case if I wild.com, because I may, and now I'm opening this wild.com and just looking at the first carbon, and instead of 2 I put 20 just to check that something will happen. Escape WQ, and now I can go back to Gauss view, file, open wild. It's really wild. You see the carbon is really far away and bonds are crazy. When the model has been created by human hands, it may or may not be ideal, right? Because not of us are professional chemists and we can do things which are not ideal. The standard way is to do so-called optimization of geometry, when algorithms based on correct interatomic forces place atoms in such interatomic distances and angles that will minimize total energy. And basically, it is what I'm going to talk on Monday and Tuesday on lectures. Just speaking about browsing to the minimum of potential energy surface and finding optimal geometry. Actual calculations are, I wouldn't, for this molecule, everything is cheap, but I want to show extra cheap thing, which is not quantum calculation. It is just use of the database to find more or less reasonable geometry, quick fix. So there is a broomstick button which tells click, and click, and it immediately brings it to something that it thinks is reasonable. I wouldn't say it is very reasonable, but at least the distances are not like 20 angstrom, right? So it's you see this hydrogens are not ideal tetrahedral, and probably it's still a bad geometry, but better than the wild geometry I created. Okay, so please try playing the things, especially changing distances. Take the model that you have created and try expanding and contracting distance. I will make a circle around seats and make sure that everyone feels comfortable with modifying distances and saving files. Okay. Just say okay. If you no, you need to do it once again. And now save, file save. Select a name. Just you need to type a name. My best molecule.
So
Yeah.
you said PDV.
Yep. Save. Now let's go to the MobiX term and see if you can observe it. You put $. It should be not $, but ampersand. So $. Will not type. If let's try Control C, it will kill the Gauss here. But now you can do ls. Enter. You see this new model, right? And type more space, new model. You can hit tab and it automatically, yeah, enter. Okay. And now you can open Gauss View once again and try reading it back. Yeah, my pleasure. Everything worked well?
I think so. Oh, I forgot to put in the file name.
Okay.
How do I get out of this again?
Escape. colon WQ. Try just Q exclamation. Escape colon Q exclamation.
Okay.
Yeah, and you can try manipulating them.
I'll see these atoms here, but it doesn't show up here. It's like
Uh-huh. No. You selected the dihedral angle, and we need this distance. So there are three things.
okay.
No,
Oh,
can you
sorry.
bring it back? Yeah, here. Click first and second.
Oh.
Yeah.
All right. Yeah.
Okay. Okay. And it should be three numbers, otherwise it will be very angry on us. Space. Just 0. Space. Whatever. 1. Okay. And originally it was water with 3 atoms. So you need another line because it will catch us in. So it was, and just do something like 3, 5, 6 or whatever. Okay, now save, escape, shift, colon, just two dots, WQ, WQ, enter. Okay. Okay, let's try just doing from scratch, maybe create new molecule, save and change one number, otherwise it is too much of human error.
Yeah.
Right now there is no rush, but as we go through the course, maybe one day you'll draw some of metal organic complex that Dr. Parentis is studying for electron transfer, right? So let's just change distance. So
This is
yeah. Next, yeah, here, click, then select first and second. Now just pull this. Okay. Now okay. And now save it as a file. Save as, save, and give a name here. Just you can. Okay, save. .com is okay for Gaussian.
okay.
Save. Now if you go here, less, more, space, test.com. Dot. So it has 2 carbons and 6 hydrogens. And if you change one of the numbers and then read it back, you'll see that molecule will change. Oh, beautiful. Yeah, thank you. And you know how to do this broomstick, right? Broomstick? No? Yeah. No, let's click on the main panel. There should be broomstick, yes, here. And now return back. See what it did. Sometimes it did errors. It's not a true method, but it's better than it was before.
Okay.
Yeah, thank you. Okay, and can you show the molecule just in Gauss view? Okay, yeah, beautiful. Thank you. Okay, save. And if we now I'm going to Control C, it will stop Gauss U, but you'll rerun. So here are your models, right? And there is a model. And if we do Gauss view once again, don't forget this ampersand. You can go there and read your file back. Okay. Yeah, thank you. All good?
Yeah.
Okay, thank you. Sarah, how are you doing? Can you show something on some molecules on your screen? Or you already closed it? Okay. But what is your subdirectory? Let's go there. No, just let's do CD. LS. Oh, yes. You need to do the same that everyone is doing. So type gview. gview dot exe shift ampersand. Yes. Okay. Yeah. Thank you. Okay. Yeah. Looks great. Yeah. Thank you.
So I was able to modify that to be like 20 position.
Okay. Can you click on the broomstick and see what happens? So now it comes to something that Gauss believes is more chemical. Okay. I'm going to stop sharing for a minute and ask Hanmant to share your screen. Okay, yeah, great. Can you please practice the broomstick? Yes. Okay, you see how it brings system back to more or less reasonable chemistry. Okay, yeah, thank you. You can stop sharing. So next two things which can be reasonable for a chemist is, well, of course, what I'm demonstrating right now is not a good molecule, not a molecule. It's like some short-living intermediate that will not be self-sustainable. But let's go over options. So after modify bond, there is a modify angle. I click on it and click on three atoms. So instead of two, it will be three. So it measures the angle between like first and third, where number two is origin. And okay, 190, 120 degrees is reasonable. It's like symmetric. So I can report it as a result of this broomstick optimization. But if I need to create my own molecule and I know that angle will be different, I can just modify and do the like. It's like a little has a rabbit with ears, right? Sometimes you see there are options to fix like two and rotate one, and it will create slightly different structures. So I'm saving, recording, telling OK, and then save as. Very wild. So please try this angle change. And in addition to angle change, there is another degree of freedom that is important for not only chemists, but also polymer scientists. And well, it's for everyone, but it's mostly evident in polymer science. It is so-called dihedral angle. So I'm going to enrich model by one more group. And there are opportunities when so-called isomers, when total number of atoms is the same, interatomic distances are the same, but molecules exhibit different properties. So one of this option to create an isomer without changing actual structure is to change so-called dihedral angle. I do not know which words to use. It's only demonstration. So it uses 4 atoms. And right now, we are measuring planes where first 2 atoms are located and second 2 atoms are located. So we change and making them in plane, out of plane, or in the opposite plane. So right now it's like 19 degrees, but if I rotate, you see there is this out of plane motion. So like if it is 0, near 0, it is in the same plane. If I rotate, these groups go out of plane. And sometimes optimization will not bring us to a right isomer, and we may need to make this modification by hand. So by doing these manipulations, we get more degrees of freedom to create any molecule that we need. Okay, and I can save as very wild number 2. Version 2. There is a thing that I always miss, but I'm missing to quickly demonstrate. But let's plan that some of you will select and report the following thing: how to copy paste molecule several times and create a model of repeating units, which will be important for those of us who need polymers. What else we see in this thing? There is so there is a way to delete atom, which we may need. So if I hate this hydrogen, I can delete it, right? The smart chemical name will be like change saturation, dehydrogenate, stuff like that. And then if after that we can do re-optimization by broomstick, the angles will be different. There are standard fragments. So if we need one of the typical groups that are standard and known, we can just borrow them from this little database. So if you think that any of these elements are close to what you need for your research, instead of clicking and drawing, one can borrow it. And probably the biggest and most beautiful is fullerene, the carbon 60. Right. And there are also like standard radical groups, like nitro group, which is responsible for explosives and oxidation, and one can add it to the fullerene. I'm not sure if it is a realistic thing, because my original background is not in chemistry, but like you can design explosive fullerenes, stuff like that. So just explore all the things. We will try to make fair share that it is well represented, and look through to maybe just explore, like there are amino acids and the basis for DNA. So there is a way to put part in a clipboard and then paste back. So if you explore and report it, it will be really cool. And some of us may use it towards projects at the end of the course. Let me go back. New model, and here let me open one of these little models and save it. File, save in the PDB format. PDB. So, so there is a file which ends with PDB. And you see it's slightly different from the Gaussian format. If I look for Gaussian format, it's same number of rows and same coordinates, but in PDB, it uses less digits, and it adds additional specifics, like it numbers all atoms, and later on it uses table of connectivity. The PDB is a little bit more standard format, and it is not protected by legal team of Gaussian. So Gaussian is a good program, but they are trying to protect their benefits through legal terms. Like if when you get to use Gaussian, you sign that you will not modify code or borrow ideas from the code to do another codes. And some researchers decline to do it because they really want to do modifications. And this also there are restrictions on using files generated by Gaussian in translation to different formats. So using PDB is not protected by this things, and therefore it's more universal. So Babel, which Babel? So it's installed somewhere in user bin. Man Babel. Not like, it's not manual. And then it tells much more than I can ever tell. So it's so Babel is not only translator; it also makes some manipulation on the molecules, and one can do wonders with Babel command. Babel minus H. So this is a very brief help, and it gives a list of formats. You see, it's around 100 different formats. And I'm going to do a little exercise, and then maybe make sure that everyone can do it as well. So Babel minus I, which stands for input, then PDB, then the C3 H7.pdb minus output XYZ C3H7 prepin XYZ. So one molecule converted, which is good. Before, when I was doing list of molecules arranged according to time, I've got 1, 2, 3, 4, 5 molecules in my subdirectory. Now I'm going to do it once again, ls minus LT. So you see, I'm getting one more file, right? There is a new file code C3H7 propene.xyz created at 18 hours 42 minutes, which is about now, right? So if I look inside, it will be the simplest possible format. And it tells the following information. So there are 10 atoms, 10 nuclei. Here is just source name of where it was taken for. And then there are 4 columns. First lists element, second lists X projection, Y projection, and Z projection. So there is nothing simpler. And it's basically the only information we need to process the model. The rest are just add-ons. So shortly, I'm going to make a visit and ask everyone to practice, save your molecule in PDB and convert it from PDB to XYZ. So please try it. And I'm going to make another demonstration. Copy, chat, paste. So just doing conversion by Babel from one format to another one is a little boring, and you can express concern that you do not believe that it does anything. It's just numbers on a screen. How do we know that it does something real? So JMol is a free piece of software available for download on your personal computers. It is a very beloved tool of biochemists. And it has a lot of options. There is a command line where one can, when this JMol is used for like 20,000 atoms biopolymer strand, it may help to represent them not as a balls and sticks, but as a ribbons, as typically people in biochemistry do. But here and I'm using on this photo an obsolete version, because sometimes unupgraded versions is not better than previous one. So it's very basic functionality, but it serves only to view the molecule created by something else. And here I'm opening the file that we originally created on Gauss view, then by Babel converted into PDB, saved as a PDB, and then by Babel converted into XYZ. And then we open this XYZ in JMol. So let me stop with this little presentation here and make us another walk around seeds and make sure that you can convert chemical atomistic models between different formats using Babel software. This Babel software is best used in a command line, and it has a much better functionality. But some of researchers were already grown by mouse-operated things, and they really hate mouse-operated, not mouse, command line. If it is the case, which I do not support, but sometimes things happen. Babel is free, and one can download and put it on the laptop in the graphical format. So it will do the same work, but then you need to download file from server to your laptop, convert, put back on server, which may or may not serve your needs well. But Babel is universal software that is free, and you can download it. Okay.
This is a comment.
Yes, yes, you use everything perfect. Let's just open thing with. Let's type tilde slash wavy line.
Oh, so.
Let's see what happens. It doesn't want to do it. Oh, yeah, we need to not ls, but just. So you recognize your model, right? Okay. So successfully converted. Okay. Yeah, I have no doubts that it will work. Okay,
I was able to give, I did the conversion from the PDB to XYZ,
Mhm.
and then here we have it.
Perfect, absolutely. Cool. Let's check, but let's try. But here we are fighting with a team of attorneys that serve to Gaussian. They don't want us to. Let's go back into Gauss view. Just open your Gauss view. %.
Should I save as?
Yes, save as PDB. Uh-huh. Okay. WQ. Yeah. And now let's practice Babel for it. Babel space minus I PDB space minus O XYZ and repeat. Yeah. Dot XYZ. Okay. So it's, you can look just more space dot XYZ. You know, try to open it with JMO. We need to set up a path. So let's tilde wavy line. Yes, slash uppercase J. Let's after you type J tab, it will probably continue. And now type lowercase J mo dot sh space, and then the name of your diethylamine dot xyz ampersand. So without this shift 7 at the end, now you're like executing two Okay. Yeah, excellent. Thank you.
Sue has GB.
Okay, yes, good. Okay, now let's go to command line. ls. Now you have this test 2, right?
Yeah.
Now Babel space minus I
Minus
minus I pdb space test 2 dot pdb minus o xyz space test 2 dot xyz
dot
xyz enter. If you are trying to convert a molecule with multi-fragments, it will take longer time.
Yeah.
So it's yeah, it's our patience is not as big. Let's just stop it. Maybe right on the background. But we can open just original file, so you see that you can open it in different piece of software. So the molecules without a connection are a little sometimes make a problem to Babel. But here is you think when I actually save it as XYZ maybe 2A XYZ and save it as so it is. It has been saved. Can you open it in JMO? I hope. Yes. Tilde slash uppercase J, hit tab, lowercase j, hit tab, type sh space, name of your file, which is like propene xyz, space, shift ampersand, shift 7, this, I don't know how to call this symbol. How do you call it?
I call it like the and.
Okay, and, okay, enter. So here something appears, let's navigate to it.
Just get closer to this one.
Do you recognize, is it your molecule?
Yes.
So it recognizes your this simple format. Okay, thank you. Oh, you didn't You can save it. Yes, this one. But, no, here. So we do have this PDB file, variable input PDB space C for PDB minus output XYZ XYZ. What? It's not happy. No, it tells molecule is converted. It's good. Okay, LS minus OT. So there is a XYZ more C4 butene XYZ. So there is a molecule. Now I can go to this JMO and open it here. You're recognize your molecule, right? Okay. Yep. Save PDB. Okay. Now in the you can look here. I'm fine. Thank you. So there is this PDB file, right? Now we can do Babel input PGB PGB minus output XYZ XYZ. One molecule converted. You can open it first as a text, and we can open it so it's your molecule, right? You recognize it. Thank you. Okay, I see everything goes well. Yeah. Okay, molecule convert. And now let's run this JMO, right? I like it. You like it. Thank you.
I'll try to be able to get.
But did you get the So I do not see XYZ files. Minus I. Minus I. No, upper arrow up, and now space, and give name of the output molecule.
That, okay, that would explain why that didn't work.
Enter. Okay, let's look more. Space and the name of this molecule of this file. Okay, and now let's open it with JMO. So it's, if you click here, it should. Do you recognize it? Okay, yeah, thank you. My pleasure. Hanmant, would you like to share screen? Okay. Were you able to open it in JMO? Okay, excellent. Super. Thank you. You can stop sharing. So, by the way, in JMO software, one can do similar operations. Someone was speaking. No. So in the JMO software, one can do similar operations by measuring distances. So clicking on pair of atoms, add to measurement list, and it can measure, it can display several interatomic distances. So if you prepare a figure for publication, it can be reasonable. And there are ways to also measure the angles. Just click on 3 atoms. And also it has this dihedral. So we need to select four atoms to practice it. 1, 2, 3, 4. Add measurement. So for this group, it shows 0 dihedral angle. Sometimes when one prepares figures for publication, one may need to number atoms and then to describe what we have by referring to atoms, like distance between carbon 3 and carbon 1 is 1.78. Because otherwise, if there are multiple carbons, what we are talking about, and independent of what our scientific merits is, reviewer will tell, I do not understand, or I pretend that I do not understand you, therefore reject the paper. So it's better to be specific. Sometimes for other purposes, instead of numbering, one can just remind the audience that gray spheres are carbons, right? And there are there is a thing that typically skipped in other pieces of of software, the lines between atoms here and do not necessarily mean bonds. So I'm going just to make a little illustration that shows that this cylinders between atoms or lines between atoms only just visualize. And there are thresholds, like one can pull the bar and tell, yeah, here all carbons are connected to all hydrogens, which is not right. We just put this bond tolerance. Right? And if you make it too small, then it will like show there are bonds where they are needed or not needed. And there are a couple of just visual effects. So some people may say your bonds are not visible. Here you go. Here everyone will observe these bonds, right? And same for atoms. There are like, depending on personal preferences, one can manipulate. And I'm not going to make circle because it's just visual effects, but who knows, maybe sometimes you like it. Okay, so let me, we already invested about 2 hours and I think it is about right to finish now. Let me quickly think what, or give a prompt if we are missing something important. So the plan is that we have one more meeting on this subject, and then it will be time for presentations. So coming Monday, let me check the dates, and it will be another demonstration of the use of the Linux. So calendar 22. So coming Monday is 31st. Then on the February 2nd, we'll do one more training. And I suggest on, so objectively, there are no days, lecture days when everyone can come, right? But you probably should make part of presentations on Monday the 7th and part of presentations of Monday the 8th. I know that there were a couple of attendees who doesn't like both Mondays and Tuesday. Payment, would you be able to come at least one of those? Or it, okay, good. So then we'll do a schedule and so that everyone has chance to present. And maybe at least a week before we will do, we'll practice like democracy and everyone signs a subject that he or she likes. And if there will be like more than one for certain subject or no one for another, I'll help to distribute evenly, but trying to use your elective vote as a primary base. Homework. So do you remember in the lecture notes, I was asking you to complete drawing of quite complicated object, right? So let me bring, if anyone rushes to the bus or to leave in like few minutes or plus minus minute, doesn't matter. Is it okay? Okay, so I'm going to pull the notes from our last lecture and bring up the slide with the homework. should be here. So probably on coming Monday, we will fill this form like people did in previous years, and I will make sure that number of subjects is equal to number of attendees. And this is just basically summarizing what briefly, very briefly, what we did in the lecture. Yes, this one. So this figure is quite busy, but it is a little simpler than it looks like. So what I'm asking you to try as a homework towards next week, and please do not worry, do not panic. I understand that it is challenging. I understand how a human hand can be imprecise. So I just want to see how you get the skill and what we are missing. And at the one aspect, and on another, that you observe your strengths and weakness and see where to progress. So this is one model, just looking from different, like in engineering blueprints, different projections. So this is a cylinder made of carbons, and this is referred to as carbon nanotubes. If to be specific here, I'm using carbon nanotubes, nanotube 11,0, which is just good tube that I like. But anything with ,0 would be cool. If you will be easy if you do something where two indices, if the second index is non-zero, the model will be much bigger. Then here, what's the name of this molecule? When to benzene ring, you add NH2 group. NH2. Yes, aniline. So we are placing aniline near a fragment of carbon nanotube. And this is a reactant for a specific reaction. And then there is I'm just bringing it in because it is ongoing research in collaboration with some nationally recognized facilities. It's a live research. Here, the reaction went and aniline get adsorbed to the surface of this cylinder. But there is a formation of carbon-to-carbon bond at the surface of nanotube, and the hydrogen that departed from aniline did settle to another spot on the surface. So building this model is a challenge. Just try your best. If you really want to succeed, do not spend more than half an hour. Just do whatever you can do in half an hour and then give up. That's normal. If you really want to succeed in it, try the thing that we didn't do here, but try databases for getting pre-made carbon nanotubes. Otherwise, it will be a torture. And there are online builders for nanotubes. You just type in Google, builder of nanotube. Some of the software like Avogadro and do have nanotube builders. There is online builder which is called CubeGen. You just tell my tube is 11,0. I want 4 unit cells, and it will just bring this piece to you. And then you just need to draw this molecule in place in a certain distance. So try doing it. And what's the best format? Maybe if you can place model in your directory on Photon, and if you really want, you can also make like screenshot, put it in PowerPoint and send it as a file, so that I see if you get to there. When we come to the end of semester, some of you may select this subject as a potential research if you do not have better ideas. So if you want a little story, carbon nanotubes are much stronger than steel. If we ever want, did you watch Foundation TV series based on Isaac Asimov? It's really novel, and it is like futuristic science fiction, like many thousands years ahead. And it has like galactic empire that disintegrates and blah, blah, blah. But one of the technical things, they have orbital station with orbital elevator, where on geostationary orbit, where our satellites for TV are sitting just above the surface, is connected, like there is a station connected to the surface of the Earth by an elevator. And instead of launching and landing rockets, people just travel there, and it takes much less energy to depart far away from there. So from engineering point of view, such project is not doable in next like centuries or millennia. But if one would do, steel and any metal will fail. So carbon nanotubes is a candidate. So it's really strong. But in the project here, carbon nanotubes are not subject of mechanical properties. They are subject for optical properties. They're really good in absorbing light, in controlled conductivity. And the only thing was missing until recently is photoluminescence, because there are processes that quench their optical properties. But if one adsorbs aniline or some few other groups, they become really bright. They become bright not in the visible, but in the near infrared. So become really bright infrared emitters in the telecom wavelengths. And also they emit not just any noisy photon, they emit high quality single photons that can be used for secure communications and for quantum computers. So building this model has like implications for bright future of the globe, saving everyone, and it's cool. If you're just curious why this model is selected. Anything else to cover now? I think it is, yeah, Sarah. Please do. No more than 4 unit cells. If you use builder, it will ask number of unit cells. If you do yourself, just look here, like 1, 2, 3, 4, maybe 5 carbon rings. But doing it by hand is impossible. Also, if you really want to do it, you want to invest no more than half an hour, and you realize that it is not doable. Just replace carbon nanotube with a graphene flake, which is like several benzene rings are arranged in a flake. And I think Gaussian already have these flakes as a pre-made structures. So it's a way out. It's a little less challenging, and I think it will be fine. So any questions on the material that we covered today, or on the homework, or on general organization? Questions 1, questions 2.
Dr. Kelly,
Any questions from Anand?
how we can transfer? How we can
Anand, any
transfer?
questions?
Yes.
No? Okay.
Yeah.
Then meeting is dismissed. Adjourn is announced. Have a nice rest of the week, and looking forward to see you on Monday if your schedule allows, and for Tuesday to those who Monday are not possible. Okay, I'll stay here and slowly close the connection, but if you want to chat something about, feel free to stop by. If no, feel free to leave. Meeting is done. Mm-hmm. Right.